collision comes in the form of a user-friendly GUI. We'll click the buttons to guide you through the process. And what it does, it interfaces with two main codes. First of all, MolPro, some chemistry package, which is used for providing molecular target orbitals, geometry optimization, various geometric properties of the target molecule. And also the UK Armstrong Plus code of molecular Armatrix suite of codes, which is the area of expertise of Stenek and Jonathan over a long number of years. And this code is responsible for calculating, ultimately responsible for calculating the cross section data. So what can QEC actually calculate? It calculates cross sections and rates for various divisional processes, including elastic scattering, momentum transfer, also various excitation processes, electronic, rotational, and vibrational excitation cross sections. There is also a method in QEC for estimating dissociative electron attachment, which is different from actual nuclear dynamics simulation, but it's an estimator of EA cross section rates. And there's also a binary encounter with beta method for calculating ionization cross sections. So to go into a bit of our matrix theory, with Stenek outlined earlier. So our matrix theory divides space into inner, outer, and asymptotic regions. So the inner region is responsible for confining the, in this case, general n-electron target molecule, its charge density, as indicated by the picture here. So this red sphere is the inner region containing target molecule inside. This usually extends to maybe 10 or 12 atomic units. And then beyond this region, you have the outer region, where you can model a single outgoing electron after the collision process. In this region, short-range effects, exchange and correlation of the outgoing electron with the inner electrons collected. You're solving a Schrödinger equation for one outgoing electron. And then at very large distances, usually 100 Bohr, the outer region wave functions are then connected to analytical known asymptotic forms, sines and cosines, as I'll show. And with this connection, then calculate observables the cross sections. So just to go into a bit of the theory, for the inner region, you're solving an n+1 electron time independent Schrödinger equation. So general n-electron target dividing electron. With this form of wave function expansion, the main things to take from this are the functions phi labeled phi I n. These are the states of the target. They are functions of n position vectors for the n electrons of the target. We then got the function for the extra electron. And then the second term is an attempt to capture correlation effects. So this is a function of not just the n electrons of the target, but also of the n+1 electrons. So with this one, you can create some sort of correlation effect between the static electron and the target electrons. And the use of MolPro here is used to generate the target wave for the basis sets and orbitals for the target. In the outer region, then, you're just solving for one outgoing electron. So what you're solving for are these functions f of the radial coordinate of the n+1 electron. And then you have these functions, which essentially handle everything else. They're known. They handle the position vectors of the n electrons of the target and the angles and spin variables of the unit. You're trying to find these functions. This. Then at large distances, usually 100 atomic units, the solutions that you get in this region are connected to known forms. So they can be connected to forms like this, sines and cosines, or plane wave type things, where the cosine term is multiplied by the K matrix. And from this K matrix, you can derive total parameters such as phase shifts, which give you interpretive information on a scattering process. So these methods can be implemented in various different forms. In particular, you can implement this expansion in the inner region in a few different ways, and different scattering models that you can adopt. So the first one is known as static exchange. And in this method, you treat just a single target wave function, only one of these phi n. Previously, there's an I here, you could have multiple such states. Here you just got the one. You still got a form out here that handles n+1 electrons. But in this approximation, in addition to having just one of these phi n's, these functions are taken as a product of a single target state and scattering electrons occupies a virtual spin orbit. With this approximation, you can't treat electronic excitation, which is only one target state. There's no excitation of the target molecule, which means you miss out on important physical phenomena such as Feshbach resonances. You can get shape resonances, but not Feshbach resonances, processes mediated by electronic excitation. And you also miss out on target polarization because by virtue of taking products of target state with the continuum electron states, you neglect polarization. So to go one better than that and actually include first step polarization, you can use the SEP method, static exchange plus polarization, where everything stays the same, except that now in these functions you include, in addition to just target state, you include single electron excitations of the target within those functions. This allows you to capture both shape and Feshbach resonances, and allows you to take account of short-range polarization effects. It doesn't, however, explicitly account for electronic excitation. So if you want to go one better than this method, you have to go to the close coupling method, where you include multiple target states here. You have a range of these target states, and you then move to things like complete active spaces, more complicated forms for this function. So this allows you to get shape and Feshbach resonances, and you can extend the energy range as well beyond to the first, depending on how many excitations you've accounted for this method, you extend the energy range up to the last one that you completed. There are additional methods extra to this, are pseudo states, but those are not methods in quick. So these three methods are the ones that have. And so this is an example result for a sort of classic system of methane. And these are comparisons of the elastic scattering cross sections that you get from Quick compared to some reference data. So a few years ago, this paper was published, which had some recommended data sets compiled from all the various experiments done on methane. There are numerous experiments. This is the sort of recommended elastic scattering cross section given by the red dots. So the three Quick calculations done with the three different methods. So this curve up here, the green dot dash line is static exchange. Static exchange plus polarization is this dashed line. It's the solid curve. So what we can see is that changing the degree of polarization and excitation that you have in the calculation really affects the low energy scattering cross sections. And in particular, this is a good case because you have two features of interest. You have a minimum down here, Ramsar times a minimum low energies. You also have this resonance up here or up here in one calculation. So this is a good case that shows that both these important features can be captured in different ways by the different calculations. Static exchange misses the minimum. It's a long way to fall by virtue of its not treating polarization. Once you include some polarization, then you pull it down to some extent. Still doesn't get the minimum, but you pull it down, so polarization is important in this region. Then by doing extra excitation, close coupling method, you actually do resolve the Ramsar times the low energies. Then at high energies for these resonances, first of all, in SE, you don't get the resonance at all. It's just the curve just continues there. So you miss it. Then with SEP, you do get this resonance out here at about 13 eV. And then the close coupling, you get it, say, at about 10. So you get different positions. But they appear in the close coupling and the SEP, which is bigger than the Feshbach resonance. So you can get those just in different positions depending on whether you use close coupling or SEP. So that's one thing to bear in mind. One thing further that you look at when you're dealing with resonances is to look at the eigenphases, which are output from Quick. And usually the eigenphases give you an indication of a resonance. So a classic sort of picture of a resonance in the eigenphases is this jump by pi or so in the eigenphases. The point about this is that you can resolve the symmetry associated with the eigenphases and then attribute the resonance to a particular symmetry. So it's an extra analysis tool that you have for analyzing, particularly for analyzing resonances. So why resonance is important, in addition to them coming up with the elastic scattering cross-section and transfer as well, they're important for processes such as DEA, and vibrational excitation, but particularly DEA. So in this example for methane, this is the estimated dissociative electron attachment cross-section for methane. This dissociative electron attachment process. And again, this is a recommended data set based on a compilation of various experiments. And then these are two quick, it's all three quick calculations. So first of all, close coupling does a reasonably good job. The resonances appear, or the DEA cross sections tend to have this sort of Gaussian looking form where they're centered on the position of the resonance. So the CC calculation gets the resonance in approximately the right energy compared to experiment. SEP is a bit higher, so it seems as if it's off. So you improve things by going from SEP to close coupling. And of course, because static exchange didn't see a resonance at all, it gets zero cross section. So it's not going to model these flashback resonance induced dissociative electron attachment processes. So that's one sort of example of how the sort of results you can get from Quick, and then some analysis tools may be useful. So the actual practical implementation or the use of Quick. So Quick comes as a GUI interface, which can be simply launched. And this is the sort of first screen that users will see when they actually launch the application. So the file menu gives you a whole bunch of options. New will allow you to start a new molecule, which is the most important. But then you have a range of other options. If you have run QEC calculations before, you can load the data you've input from the previous calculation. The first step in setting up the calculations is to enter the geometry for the target molecule, equilibrium geometry. And you can enter this by hand, say by using this data, and you can enter it into the GUI, as I'll show on the next slide. You can also load the geometry file of coordinates, which can be handier for 3 molecules. And there are a set of examples to sort of get users to practice with all the various functionalities of the code. You can also look back at previous results. If you've generated results, previous calculations, on the back of them from this first screen. So this is then the next screen that comes up. This is where you can enter the geometry of the target molecule. So it's simply a table here. I've loaded methane. Extra atoms can be added. There's an add atom button, and you can enter these. These are the coordinates dimensional that you can get to this data. All of this data will be entered. If you load a geometry file with sort of CSV file with all this information, this will simply pop up. You can then optimize this geometry with Molcode and center to make sure it's actually at the center of that the origin is the center of mass. That's actually an important feature. It's one of the assumptions of the method. So if it doesn't do that automatically with Molcode, sometimes it does. If it hasn't done it automatically, you can center it here. And then this gives you extra information about bond lengths and angles and so forth. Correlate with missed data. So then the next page in the setup will allow you to enter orbital types and basis sets. These are options in Molcode, which are used for expanding the wave function. We'll also give you a picture on the left-hand side of the molecular symmetry and its point group. The only thing probably to note from this is the Molcode uses helium point groups. So for diatomics, you get D2H, so we kind of get C2B here. But it will identify the point group and then select the orbital type and basis set. Only thing to be careful of when selecting the orbital types is that the Hartree-Fock orbitals are to be used when you select the SE and SEP methods, because the single target state you use there is generated from Hartree-Fock calculation. So you have to select Hartree-Fock orbitals if you're going on to use SE or SEP. If you're going to use close coupling, then you have to select the MC-SCF. It's multi-configurational self-consistent field orbitals option. So there's a bit of planning that needs to be done at this stage. You know whether you're doing close coupling or not. And then for basis sets, there are sets of basis sets that you can select for use of MoPro. We have the main ones in there, Dunning, Opal, and also college basis sets are available. They can be selected just from a drop down menu here. There are some advanced options as well for slightly unusual systems, particularly for ions, for radicals, and possibly for large systems as well. So when you select the advanced options, you can use an ECP if your molecule contains heavy elements, the iodine, something like that. It may be difficult to treat all electrons. You can use an ECP for ionization calculations. They're not included in the R matrix method in general, but you can use them in conjunction with the binary encounter beta formalism for the ionization cross section to reduce the size of the calculations for the ionization cross section. You can impose a charge, spin multiplicity, and the symmetry. That's particularly useful for radicals, obviously. Doublet initial state. And you can also select a maximum memory for the MoPro calculations. MoPro requires an input in megawords, and the default of 20 is usually sufficient for most things, but you can enter up to 999 there, should you so wish. So these are the advanced options when you're using partial fault orbitals. If you're using MCSCF and you're going to do a close coupling calculation, you're going in active space, then you've got additional options for entering things here. So for the MCSCF calculations, you need to know what orbitals are closed, what are going to be doubly occupied, and then what orbitals are going to be active and have not necessarily going to be doubly occupied in your active space. Default will be set here, and that can be changed by the user at runtime. So you then progress from the next one is the R matrix setup. So it'll be a picture of your inner region. The main thing to find out here is your inner region big enough? So you can select from this drop-down menu R matrix sphere sizes of 10 and above, up to 14. And this picture will adaptively change to tell you whether or not your sphere is big enough to maintain the charge density of the target molecule. At this point, you select the method, SE, set, or continuing, and then you define a scattering energy grid. This is the default one, which usually doesn't need to change. And usually we'll calculate cross sections up to about 15 dB. So that can be entered by the user at this point. If you select set, there are some advanced options in here. A couple are grayed out, which I'll come to in a minute because they will be applicable to close coupling. But you can have extra virtual orbitals that just increases the sizes of those expansions of the wave function that I showed earlier. There's a default number of virtual orbitals which can be changed to the grid. That can be changed by the user as well. And then you have close coupling. Close coupling does have some extra options. You can, in your close coupling calculations, you'll be calculating excitation cross sections. For some systems, you may have a lot of excited states. Usually, it will calculate however many there are in the energy range that you specify. So it will calculate by default all excited states below 15 eV. But if you encounter a case where you have a lot of target states, or a lot of excited states, you can limit it here to a certain number. You can also limit the vertical excitation energy. So you only calculate excited states up to a certain energy rather than up to 15 eV. Should the number all of it 15 eV be too difficult to calculate? And you can also impose a number of virtual orbitals in this case as well. Then you come to the final page, which is actually selecting the cross sections you want to calculate. By default, this is the either SE or set calculation. There's a standard set of R matrix cross sections to calculate, which are the total elastic scattering cross section, and by default you get the eigenbasis as well. Here it's grayed out, calculating excited state cross sections, because this is either an SE or set calculation. You have those, you get included excitation, and you also get binary encoded beta ionization cross sections. If you wish, you can add differential cross-section, momentum transfer and rotational excitation, vibrational excitation, and also the DEA estimation method. You can run small convergence checks as well. There is a check for running calculations for armature sphere geometry, so you want to check test convergence. So with the calculation with respect to different armature size, you can take this box and enter different armatures near region radii and run two calculations. Another way to do that is actually set up next to job. So previously, if any of you used QEC before, usually at this point you clicked run and ran a single calculation, produced results. And you then waited until the results are out before starting the next job. If you so wish, there is a set up next job button now, which will take you back to the beginning, enter a new molecule or new parameters for the next job, and continue. The jobs will queue then and run sequentially. But these are the main options for cross sections. Just calculate the page. If you're doing a close coupling calculation, then you have excited state cross sections enabled. If you're using the DEA estimator method, there's one other thing that pops up at this stage, and that is to enter parameters. The estimator requires input of certain parameters, association energy, just bond association or bond breaking. You have the dissociation energy of a bond, a vibrational frequency, which has a default value, but you can specify, you know it, the fundamental vibration frequency, which you can get from this. And then have to input the assumed breakup and the electron affinity of your second fragment. So just those are parameters about which you can calculate the associated attachment cross section. And so yes, just maybe the final thing to highlight here is the change going from previous incarnations of QEC, where you ran one job at a time. Now we've set up each job, which allows you to set up a queue of jobs, which will run sequentially. So this is a picture of the output from the calculation. When you click run and the calculation begins, you will get a printout of a log to the GUI itself. So this is just the very start of it. It's just the molecular information. It gives you the molecule, the charge, the coordinates that you've entered, the point group, and various other properties and stuff listed all of down here. It will then progress through various stages of the calculation and give you timings for things. And the expected time, it will give you an idea of the progress as it goes. It'll tell you what routine it's running on, how long it expects based on the time taken from previous routines, how long it expects to continue to run. And then some other information towards the end. And it will tell you if it's completed successfully, if it's legible. In the back, I doubt it, but here it says calculation completed successfully. So you want to see, and then what will happen for each job that you run, you'll get this pop-up window from which you view the cross sections calculated. The view graph will come up showing your cross section. And the reason there are two here is because obviously I ran two calculations using the setup next job feature. So I run one calculation, and when the results are output, they're not only output here, they're also print. All the files are sent to a directory, and the directory is named in this handy way. Again, I don't know if you can read that from here, but the directory is named as the molecule, the base set, the method, the orbitals, and the armature sphere and the timestamp. So I run two calculations here, and the only difference between what I see is that this one says 14, this armature sphere is 14, this one says 10. So I run different armature spheres to check convergence. And in each case, it will pop up with a window here. So if you run several jobs, if you wait until the end, the results will all pop up in a separate window, and you can compare that. So in addition to actually running the calculations as a starter, who's starting to use QEC, there is a suite of examples which covers most of the main features of QEC. So there's a directory with simple SE examples, which will give you a calculation or give several calculations that use the SE method. There are simple and advanced close coupling methods to try, which the simple ones probably are quick and straightforward. The advanced ones probably just the more advanced because they take longer to run. So there's more detail in them. And there are various other examples of DPA. There's a web example of ECP, so it's probably for CH3I, something like that, perhaps. And then there are other examples for cell, for the user to try as a sort of initial step with the code. So that brings me to the end of my talk. I'd just like to acknowledge my co-workers at Quantemol. In addition to myself working on Quick, I also get assistance from time to time from Karen, who is now in Nebraska, and also from Katerina, who mostly working on machine learning, but she can turn her hands to Quick calculations as well. And I should also thank Stenik, because we have worked with Stenik and collaborated on things, and it's always useful to have his expertise on things as well. So thank you for your attention.